Before we proceed with this lecture, I request you to watch my previous video on complex number part 1 to understand basic things about the complex number. In this lecture, we will discuss number 1, square root of a complex number, number 2, modulus and argument of a complex number, number 3, polar form of a complex number, number 4, exponential form of a complex number, and some representative problems based on these concepts. Hello friends, you are watching YouTube channel Number Collage. This channel features videos on mathematical concepts. Effort has been made to explore the concepts through basic mathematical ideas. Hope you will like my effort. We will start our discussion by understanding what happens to higher powers of I. As we know, complex number I is square root of minus 1, so that I square becomes minus 1. I cube will be I square into I, that will be minus 1 into I minus I raised to 4 will be square of I square, that is square of minus 1, 1. I raised to 5 will be I raised to 4 into I, that is 1 into I. What will be I raised to 52? We will express it as I square raised to 26. It will be minus 1 raised to 26. Minus 1 raised to even power is 1. So I raised to 52 will be 1. What will be I raised to 63? We have to write it as I raised to 62 into I raised to 62 will be I square raised to 31 into I, that will be minus 1 raised to 31 into I. Now odd power of minus 1 is negative, so it will be minus 1 into I minus I. So I raised to 63 is minus I. What will be I raised to 49? We write it as I raised to 48 into I raised to 48 we write as I square raised to 24 into I, that will be minus 1 raised to 24 into I. But since even power of minus 1 is plus 1, it will be 1 into I. That means I raised to 49 is I. So in this way we can easily find higher powers of I. Next we will see how to find square root of a complex number. Suppose we want to find square root of complex number x plus iy. We will assume it to be a plus ib. After squaring we will get x plus iy equals a plus ib whole square, that will be a square plus 2I into ab plus I square b square. But since I square is minus 1, it will be minus b square. Now we will rewrite it as x plus iy equals a square minus b square plus 2ab into I. After equating real part and imaginary part, we write x equals a square minus b square and y equals 2ab. Here values of x and y are known, so we can solve these two equations to find the values of a and b to get this square root a plus ib. Let us find square root of 5 minus 6i. We will assume x plus iy equals square root of 5 minus 6i. After squaring we will get x plus iy whole square equals 5 minus 6i. Expanding the bracket, it will be x square plus 2xy into I plus I square y square. But since I square is minus 1, it will be minus y square, which is equal to 5 minus 6i. We will rewrite this as x square minus y square plus 2xy into I equals 5 minus 6i. Now equating real parts, we write x square minus y square equals 5, and equating imaginary parts 2xy equals minus 6, that gives xy equals minus 3. That gives y equals minus 3 upon x. Substituting value of y in this equation 1, we write x square minus 3 upon x square 9 upon x square equals 5. Multiplying throughout by x square, it will be x raised to 4 minus 9 equals 5x square. After rewriting, it will be x raised to 4 minus 5x square minus 9 equals 0. For example, we will find square root of 3 minus 4i. We will assume x plus iy to be the square root of 3 minus 4i. After squaring both sides, we write x plus iy whole square equals 3 minus 4i. It will be x square plus 2xy into I plus I square y square. But since I square is minus 1, it will be minus y square equals 3 minus 4i. We will rewrite this as x square minus y square plus 2xy into I equals 3 minus 4i. Equating the real parts, x square minus y square equals 3. We name this 1, and equating the imaginary parts, 2xy equals minus 4, that gives xy equals minus 2 or y equals minus 2 by x. Now we will use this value of y in equation 1 and write x square minus square of minus 2 upon x will be 4 upon x square, that equals 3. Now we will multiply throughout by x square, that gives square of x square minus 4 equals 3x square. Rewriting this as square of x square minus 3x square minus 4 equals 0. This is a quadratic equation in x square. Substituting x square equals p, we write p square minus 3p minus 4 equals 0. This can be factorized as p minus 4 into p plus 1 equals 0, which gives p equals 4, that is x square equals 4 and x equals plus minus 2, and p equals minus 1, that is x square equals minus 1, or x equals plus minus root minus 1, that is plus minus I. So here we got real values of x plus minus 2 and imaginary values of x plus minus I. But since x is real, we will not accept these values of x. Now when x is 2, this y will be minus 2 upon 2, that is minus 1, and when x is minus 2, y will be minus 2 upon minus 2, 1. So we will get 2 square roots of 3 minus 4i. The first being this 2 minus I from this minus 1, and second root will be this minus 2 plus I from this 1. So these are the 2 square roots of 3 minus 4i. Next we will understand what is modulus and argument of a complex number. Although z equals x plus iy is a complex number, we can represent it by a point P on a xy coordinate system, where point P has coordinates x and y. Let distance OP be r. Let us draw a perpendicular from P on the x-axis, whose foot is q. From the coordinates of P, OQ will be x and PQ will be y. Let OP makes angle theta with the positive x-axis. In right triangle OPQ, cos theta is x upon r. Therefore x will be r cos theta, and since sin theta is y upon r, y coordinate will be r sin theta. Now x square plus y square will be r square into sin square theta plus cos square theta, and Since sin square theta plus cos square theta is 1, x square plus y square will be r square. That implies r equals square root of x square plus y square. Further, y upon x is r sin theta upon r cos theta, which is, after cancelling this r, will become tan theta. That will give theta equals tan inverse y by x. Here r equals square root of x square plus y square is called modulus of z, and it is denoted by mod z. So mod z will be square root of x square plus y square, and this theta is called argument or amplitude of z. In x equals r cos theta and y equals r sin theta, both x and y have been expressed in terms of modulus r and argument theta. Therefore, r cos theta and r sin theta are called polar coordinates of z, and the polar form of complex number z will be r into cos theta plus I sin theta. We will express a complex number x plus iy given to be 1 minus root 2 plus I in the polar form r into cos theta plus I sin theta. For that, we need to find the argument r and amplitude theta. Comparing the real parts and imaginary parts, we write x equals 1 minus root 2 and y equals 1. The argument r will be square root of x square plus y square, that is square root of 1 minus root 2 whole square plus 1 square, which is 1. That will be expanding the bracket 1 minus 2 root 2 plus 1 plus 1. So argument r will be square root of 3 minus 2 root 2. Cos theta will be x by r, that equals 1 minus root 2 upon square root of 3 minus 2 root 2. Sin theta will be y upon r, that is 1 upon square root of 3 minus 2 root 2. So the polar form will be this r square root of 3 minus 2 root 2 into cos theta, which is 1 minus root 2 upon square root 3 minus 2 root 2 plus I into sin theta, which is 1 upon square root of 3 minus 2 root 2. So this is the required polar form. We have to express minus root 3 plus I in the polar form r into cos theta plus I sin theta and find its principal argument. We are given z equals x plus iy to be minus root 3 plus I. By equating real and imaginary parts, we write x equals minus root 3, y equals 1. R will be square root x square plus y square, that will be square root of minus root 3 square will be 3, 1 square will be 1, so square root of 4 will be 2. So r is 2. Next, cos theta is x upon r, that is minus root 3 upon 2. Sin theta is y upon r, that is 1 upon 2. Principal argument means that value of theta which lies between minus pi and plus pi. Now here cos theta is negative and sin theta is positive, which means theta lies in the second quadrant. So theta will be pi minus pi by 6, because cos pi by 6, that is cos 30, is root 3 by 2. So this gives us theta equals 6 pi minus pi, 5 pi by 6. So the principal argument here is 5 pi by 6 or 150 degrees. Let us see how to find modulus and argument of minus half plus root 3 by 2i. Let this complex number z be represented by x plus iy equals minus half plus root 3 by 2i, which in the polar form will be r cos theta plus I into r sin theta. Equating real parts and imaginary parts, we write r cos theta equals minus half and r sin theta equals root 3 by 2. Squaring and adding, this will be r square into cos square theta plus sin square theta equals minus half square will be 1/4 plus root 3 by 2 square will be 3 by 4, which will be 4 by 4, that is 1. This will be r square equals 1, or modulus r will be 1. Therefore r cos theta will be cos theta minus half and sin theta root 3 by 2. Sin theta equals root 3 by 2 implies theta equals pi by 3. And since cos theta is negative implies theta lies in the second quadrant. So theta will be pi minus pi by 3 equals 3 pi minus pi 2 pi by 3 radians or 120 degrees. So we have principal value of theta 2 pi by 3 radians modulus r equals 1 and argument of z pi by 3. How to find modulus and principal value of amplitude of 1 plus I root 3 whole cube upon 2 into 1 plus I whole square into root 3 plus I. This can be further simplified as 1 plus I root 3 whole cube will be 1 cube, which is 1, plus 3 1 square, which is 1, into I root 3 plus 3 into 1 into I root 3 square, which is 3, I square is minus 1, plus I root 3 whole cube will be 3 root 3 I cube is minus I upon 2 into 1 plus I whole square will be 1 plus 2I plus I square, which will be minus 1 into root 3 plus I. This 1 minus 9 will be minus 8. 3 root 3I minus 3 root 3I will be 0 upon 1 minus 1 will be 0. 4I into root 3 plus I. This will be 4 ones are 4 twos are minus 2 upon I root 3 plus I square, that will be minus 1, which is minus 2 upon minus 1 plus I root 3. We will multiply this by conjugate of this denominator, which is minus 1 minus I root 3 upon minus 1 minus I root 3. This will be 2 into 1 plus I root 3 upon minus 1 square, which is 1, minus root 3 square is 3, I square is minus 1. So this will be plus 3. It is 2 into 1 plus I root 3 upon 4. 2 ones are 2 twos are. So the complex number that we get after simplification is 1 by 2 plus root 3 by 2 into I. This gives x equals half, y equals root 3 by 2. Now we will understand exponential form of a complex number. We already know that complex number z equals x plus iy can be written in the polar form as z equals r into cos theta plus I sin theta, in which we will make use of expansion series of functions e raised to x, cos x and sin x. First we will write expansion series of e raised to x, which is 1 plus x square upon 2 factorial plus x cube upon 3 factorial plus so on and so forth. Expansion series of cos x is 1 minus x square upon 2 factorial plus x raised to 4 upon 4 factorial minus x raised to 6 upon 6 factorial plus so on and so forth. And expansion series of sin x is x minus x cube upon 3 factorial plus x raised to 5 upon 5 factorial minus x raised to 7 upon 7 factorial plus so on and so forth. We will rewrite the expansion series of e raised to x by replacing this x by I theta. So e raised to I theta will be 1 plus I theta plus I square theta square upon 2 factorial plus I cube theta cube upon 3 factorial plus I raised to 4 theta raised to 4 upon 4 factorial plus I raised to 5 theta raised to 5 upon 5 factorial plus I raised to 6 theta raised to 6 upon 6 factorial plus so and so forth. This will be 1 plus I theta minus theta square upon 2 factorial, because this I square is minus 1, minus I theta cube upon 3 factorial, because this I cube is minus I, plus theta raised to 4 upon 4 factorial, because I raised to 4 is 1 plus I theta raised to 5 upon 5 factorial, because I raised to 5 is I, minus theta raised to 6 upon 6 factorial, because I raised to 6 is minus 1, plus so and so forth. Here the terms 1 minus theta square upon 2 factorial plus theta raised to 4 upon 4 factorial minus theta raised to 6 upon 6 factorial, etc. represent expansion series of cos theta. So we will write these terms in a separate bracket. 1 minus theta square upon 2 factorial plus theta raised to 4 upon 4 factorial minus theta raised to 6 upon 6 factorial plus so and so forth, and the terms I theta minus I theta cube upon 3 factorial plus I into theta raised to 5 upon 5 factorial, etc. represent expansion series of sine theta. So we write these terms as plus I times, because I is a common factor in all these terms, into theta minus theta cube upon 3 factorial plus theta raised to 5 upon 5 factorial minus so and so forth. So we write e raised to I theta equals, this being expansion series of cos theta, we will write this as cos theta plus this I into this being expansion series of sine theta, but a complex number z in its polar form is r into cos theta plus I sine theta. Therefore, the exponential form of the complex number will be z equals r into e raised to I theta. We have z equals e raised to I theta, which is also equal to cos theta plus I sin theta. Similarly, 1 by z will be 1 by e raised to I theta, that will be e raised to minus I theta, which will be cos theta minus I sin theta. In other words, we can write 1 by cos theta plus I sin theta equals cos theta minus I sin theta. Also, if z equals cos theta plus I sin theta, then 1 by z equals cos theta minus I sin theta. We have to prove e raised to I pi plus 1 equals 0. Here, left hand side e raised to I pi plus 1 will be cos pi plus I sin pi plus 1, but cos pi is minus 1 plus I, sin pi is 0 plus 1, which will be 0. Since LHS equals RHS, e raised to I pi plus 1 equals 0 is proved. Now in a nutshell, we will write different forms of a complex number. First is z equals x plus iy, which is the Cartesian form. Z equals r into cos theta plus I sin theta is the polar form. Z equals r into e raised to I theta is the exponential form of a complex number. Next, by changing the sign of I, we can write complex conjugate z bar as x minus iy. Z bar equals r into cos theta minus I sin theta, and z bar equals r into e raised to minus I theta. If you like this video, please like it, share it, and subscribe to this channel. See you in the next video. Until then, keep watching Number Collage. Thank you.